Hello, everyone. I'm going to be talking about how we can combine SAT solving with isomorph-free exhaustive generation in order to solve some combinatorial problems, such as Lamb's problem. So Lamb's problem is to show the non-existence of a certain type of geometric structure. This is a very interesting structure that has been intriguing mathematicians for hundreds of years. I have an example of a small example of what's known as a projective plane on the slide here. And this projective plane has 13 points and 13 lines, and it's known as a projective plane of order 3. Okay, so the interesting thing about projective planes is that if you take any two lines, such as right here I've highlighted the green line and I've highlighted the blue line, any two lines are going to meet at one and only one point. And so here the point is represented by this gray dot here. Conversely, if we take any 2 points in the projective plane, they are going to lie on one and only one line. For example, if I take the green point and the brown point, you can see here I've highlighted that they lie on a single line, which is the pink line. So this is going to hold for any 2 points or any 2 lines. The question, Lamb's problem, is can this type of a structure exist for a projective plane of order 10? This would have 111 points and 111 lines, which is an insanely large structure, right? Just the number of ways you could try to construct this is just so enormous. You can't just write a computer program to do a brute force search. And nobody knows any way to actually construct this theoretically. Some mathematicians conjectured that it should exist. Some mathematicians conjectured it didn't exist. This was an open problem for hundreds of years. And eventually it was solved by Lamb, who was a mathematician at Concordia University. And him, along with a team of programmers, actually solved the problem using a supercomputer search. Now, here's the question. How do we trust their search, right? They were upfront that their computer code may have bugs. There's no way to verify that their code doesn't have bugs. And in fact, just by anyone who's used a computer knows computers have lots of bugs, right? So how do we trust that they didn't accidentally miss a case that led to a projective plane of order 10? This is where we come in. We wanted to generate the first verifiable resolution of Lamb's problem. And we do this by reducing the problem from a problem in geometry to a problem in Boolean logic. So we reduce it to a SAT problem and then use a SAT solver to generate a proof of that there are no projective planes of order 10, right? Because the SAT solver can generate a certificate which can be verified to show that there are no solutions of the SAT instance. Now, in order to reduce the size of the search space, we also needed to employ an isomorph-free exhaustive generation approach, as I will describe. But first, the reduction to SAT is actually quite straightforward. You just define a Boolean variable for every possible point line incidence. So the variable, say aij, represents that point I lies on line j. And then you just encode all of the projective plane axioms in Boolean logic. For example, we know that points 1 and 2 cannot simultaneously lie on lines 1 and 2 because by an axiom, points 1 and 2 must lie on exactly one and only one line. So this can be encoded as a constraint in Boolean logic like this. There'll be lots of these types of constraints. We give them to the SAT solver, and the SAT solver is going to try to find a satisfying assignment. Now, the problem is the search space is just too enormous, and it's very highly symmetric. In particular, we can permute any of the lines or any of the points freely because the axioms do not specify any distinguished points or lines. So if we consider them as points and lines as binary row and column vectors, we can say enforce a specific ordering on the points and lines. We say that the lines and points are ordered in a lexicographic fashion. This is going to significantly reduce the size of the search space without losing any solutions because we can have this, we're freely able to permute the rows and lines as we please. So we just force a particular ordering. Now this reduces a lot of symmetry. However, there are still many symmetries which still exist in the search space, which nobody has any known simple way to break, right? There's still going to be many symmetries which are not captured by this lexicographic ordering. So this is where we go to the recorded objects approach to isomorph-free exhaustive generation, and this is how it works. During the search, the SAT solver is going to be finding partial solutions. Okay, so it's finding partial projective planes, such as the one demonstrated on the slide here. So these are lines and points. Up to some point, they satisfy the axioms, but we don't know if they can be extended beyond that point. Anyways, we give the partial projective plane to a computer algebra system, and the algebra system is going to examine the isomorphism class of this partial solution. What it's going to do is it's going to generate an isomorphism certificate of that isomorphism class. And in the recorded objects approach, we just keep a record of all the certificates that we've seen so far. So every time we get a new certificate, we add it into the record. And if it's ever the case that we see a new solution, but the certificate matches a previously found partial solution, then we block the new partial solution because its certificate shows that it is actually isomorphic to a previously found solution. Therefore, since we already considered the previous solution, there's no need to consider it again, right? We found a new solution which is isomorphic to something we already saw. So we just block the partial solution. Now, why, you might ask, is this actually a powerful technique? And indeed, it is a very powerful technique. We enumerated all of the possibilities for the first 19 points of the plane 150 times faster using this recorded objects approach than to use the alternative approach, which would be just to only find all solutions and then at the very end, then remove all the isomorphisms. In the alternative approach, you would be calling the computer algebra system fewer times. However, it pays off to call the computer algebra system while the solver is running, right? It's much, much faster to make more calls to the computer algebra system, but do it sooner than it is to wait till the end, right? And so this is why we hooked up the Isomorph-Free generation approach inside the SAT solver and not just wait till the end to do the isomorphism removal. It's much faster to do the isomorphism removal inside the SAT solver, even though we're making more calls to the computer algebra system. So in the end, we were able to provide the first formal verification of Lamb's resolution. And we did this by verifying two things. First, the certificate that the SAT solver produces. There are well-known proof verifiers which can check those, basically a trace of what the SAT solver derived. And then secondly, we also verified what the computer algebra system produced. Whenever it says that two objects are isomorphic, we explicitly verify that isomorphism exists. We actually look at the permutation of permute these points to get the object that it claims is isomorphic to it. Indeed, there had been a previous, besides Lamb's original search in 1989, there was an independent verification in 2011, and we were able to verify. In the process of doing our verification, we actually found that there had indeed been missed cases in both of the previous searches. This just goes to show how important it is to actually have a formal certificate which can be verified, because it's very, very difficult to write bug-free code. And this just goes to show just how difficult it is. Even though they both were very careful about not missing cases, they did miss a couple cases. In the end, we have shown that the isomorph-free exhaustive generation approach makes a lot of sense to actually exploit inside the SAT solver. Surprisingly, this hasn't really been done all that much. We've applied this to many different types of combinatorial objects, and what we find in practice is we're actually getting an exponential speed up in the size of the object. So if you are interested in learning more about this work, check out my website. We've been applying this sort of techniques to many different types of combinatorial objects, and I will be happy to hear from you if you think you have problems where it could be useful. So thank you everyone for your time, and I'm sorry I couldn't be there in person.